Hi, my name is Oscar Cartagena. I am a PhD candidate in electrical engineering of the Department of Electrical Engineering of the University of Chile. And here I'm going to present my research topic that is called Evolving Phase Prediction Interval Design for a Fault Detection Application in a Heat Exchange. So the contents of this presentation, first I want to start with the motivational objectives of this research. Then I'm going to continue with the background methods used for them propose the prediction interval method. And then I am going to finish with the experimental results applied over a heat exchanger plate modeling and the interval-based fault detection algorithm implementation. So as a motivation, we start with the idea of the fuzzy prediction interval methods can handle the modeling of nonlinear systems with uncertainties. But the prediction intervals could have problems when modeling system with change. So we propose to use the updating mechanisms from the evolving intelligence systems to handle this problematic. So the uncertainty provided by the prediction intervals can be used for detecting change in the system. So as an example, here's the use of fuzzy prediction intervals in the case of time invariant system when the interval works fine, and from time variant system when the prediction interval could fail to contain the real measurements. Here in this image represented by the blue points. So the objective of this research are to design new methods of evolving phase prediction intervals that are capable of modeling nonlinear time variant systems with uncertainties. Also, to perform an evaluation of the proposal in terms of the interval width, coverage level, and computational cost. And to apply the proposed method to the implementation of a simple fault detection algorithm. So as a background, we start with the selection of the base prediction interval method. And in this work, we choose the fuzzy prediction interval based on the sequential fuzzy numbers. This is selected because the interpretability of the fuzzy model structure, the simplicity and versatility of the sequential fuzzy numbers method, and the good performance among fuzzy methods during the simulation test. So the prediction interval based on fuzzy number consists in the base prediction model. Here in the blue box is presented as an example, a linear model. So the bounds of the interval are constructed following the similar structure to the discrete model. So we have an upper bound for the linear parameters of the interval and a lower bound for the same parameters. So for being able to apply this method in different kind of application, we choose the use of the Takagi-Sugeno fuzzy model, where the system can be represented by the weighted sum of different rules. Rules are here. So the interval bounds can be obtained in a similar way using a weighted sum of the local bounds of the interval. For doing this fuzzy model, we apply the fuzzy clustering of the sample vector set K, which are composed by the output of the system and the path regressors of the output and input variables that enter the system. So for the proposals, we propose the recursively learning of the interval method. An alternative method of evolving prediction interval is proposed based only on this recursively adaptation. We are doing this because we can avoid high computational complexity of the offline fuzzy identification of fuzzy models. And we can maintain the simplicity and versatility of the sequential fuzzy numbers method. And also, based on the simulation test, can maintain a good performance during the simulation. So this is a summary of the algorithm proposed. We start with the first cluster initialization. Then when we have several measurements of the system, we have to compute the distance of this sample vector to each cluster in the mode. Then, and based on this distance, we can decide if we update an existing cluster or if we need to create a new cluster. After this, we need to check if the existing cluster has to be merged or one of the clusters becomes too large, so has to be split, or a cluster has been getting old, has not been updated for an extended period of time, so it could be removed from the model. For the first part, the estimation of the interval coverage, we start with a desired coverage, for example, 95%. So we propose a counting variable, xc, that tries to represent the coverage for past n samples for these clusters. So this count is going to sum if the interval contains the measurement and rest otherwise. And this count is saturated within the range 0 and 1. So in the process of selection of the cluster, originally chosen for the full mode method, now we have for the prediction interval method that we need to include the spread values of the interval in the updating of the cluster. So here is the updating of the cluster. For doing this, we consider using the well-for online algorithm to update the antecedents of the fuzzy model. This is the mean and the variance of the cluster. And the consequence updating, also known as the local linear parameters, we use the recursive least square method that is presented here in the red box. And in the green box is presented the proposal, this is the novel proposal, of the spread updating for the prediction interval. So this is an example of the evolving mechanism that we use when the sample vector is close to an existing cluster. In the case of the new sample vector is too far from all of the existing cluster, we need to create a new cluster. And then in things later, we are going to have more measurements that are going to be associated to these new clusters. This is, of course, only when the minimum distance of the sample vector among all of the existing clusters surpass a predefined threshold. The next evolving mechanism is the cluster merging. This is done if the minimum distance between centers of two clusters, considering both directions, is less than a definite threshold, and the similarity index that is related with the volume of the clusters does not surpass a threshold. So in this case, these clusters are combined using a weighted combination. So in this example, we can see that the distribution of the clusters are different. So in this case, the clusters are not merged. But in this second case, both of clusters follow the same direction, so are considered to be merged, now forming a single cluster. The next evolving mechanism to consider is the cluster splitting. This is applied only if the interval width, which represents the prediction error associated to that cluster, becomes too large. And we separate the cluster based on the aging vectors and aging values of the covariance matrix associated to these clusters. So we establish the directions based on the aging vectors, and then the principal component is considered to make the division, this splitting of the clusters. And then we have the cluster removal. In this case, we only have to take account of when a cluster is activated. So we proceed to the removal of a cluster if it's not activated for a long period of time. So are erased from the model. So here is the proposal summary. Originally, we start with the cluster initialization from sample. For the initial sample, then we estimate the interval coverage with the proposed coverage count. Then we calculate the distance of the sample vector to each cluster that belongs to the model. And if this distance is less than some threshold, the sample vector joins the closest cluster. On the other hand, if this distance is above the threshold, we proceed to create a new cluster, and then after this part of the algorithm, we proceed with the merge and split the existing clusters. And finishing with the checking if a cluster has to be removed from the model. And then we start again in the estimation of the interval coverage again, but with the new sample vector. So based on the prediction interval obtained from the previous algorithm, we propose an interval-based fault detection algorithm. So in this case, it's important to note that we need a fixed prediction interval. So in this case, we are not considering the adaptation of the evolving algorithm. In this case, we propose using a failure interval counting. So it's similar to the estimation of the coverage level, but in this case, we are reducing this count when the interval contains the measurements. And we sum a factor when the interval fails to contain the measurement. So we determine that the fault detection condition is that if this count, CF, surpass the threshold value based on the expected coverage level of the prediction interval. And we are going to apply these both proposals in the following experimental test. Here is the modeling of a heat exchanger plant composed by an open circuit of water supply network and cold water flow. And we have in the bottom part a closed circuit of hot water flow that is handled by a thermostat and a motor driving valve. So the idea is to interact with this system and obtain a prediction interval. So we use an experimental when we have to model the heat exchanger using a sample time of 4 seconds. The system modeling is trained for 30 prediction steps. That means 120 seconds ahead or 2 minutes in the future. So based on the signal in the left part of the slide, we obtain the prediction interval that can be observed in the right side of the slide. And we can see here how the interval had problems to adapt to the uncertainty of the model, but then is improving when the algorithm runs, improving the performance of the coverage level and also the interval width. Then the generate prediction interval is stored in the memory, remains fixed in this point, and we proceed to introduce some faults in the heat exchanger. The first fault consists in changing the hot water temperature in the thermostat. And the second fault is to change the openness of the motor driving valve associated to the hot water, producing this reduction in the values of the output temperature of the system, where we can see that the interval fails to contain those elements. So based on this, we implemented the fault detection algorithms. We compare first with the model-based fault detection that is based on the evaluation of the prediction error for one step. The second figure shows the same performance, but in this case for the 30 prediction steps. And we also implemented a fault detection algorithm based on the parameter clustering and a fault detection based on the input-output evolving clustering. And the last figure shows the fault detection based on the proposed prediction intervals that consist in the proposal of this research. So if we observe the alarms and when the change of the system occur, we can observe that there is a higher accuracy of the fault detection method if we use the proposal of this research. And also, based on the time window that we use to estimate the prediction interval failure, we can estimate the instant when the fall starts. That is represented in the last figure in the bottom of the slide with the yellow line. Well, as a conclusion of this presentation, we presented a proposal design that considers two main chains that a system could present. First, an abrupt change and gradual drifts. The proposed algorithm was structured based on a passive learning approach. This consists in a constant updating of the clusters. And the proposal was tested in two different cases: the modeling of a heat exchanger plant and the detection of two faults, or in this case, change in the system in the heat exchanger. The experimental results of the effectiveness of this proposal. Also, a novel updating of the interval width was proposed, as is the main contributions that this work makes. So, if you want to know further details about this research, the more details of the experimental results are available in the following article. This is the evolving phase prediction interval for fault detection in a heat exchanger that is published in the Applied of Computing Journal. Here is the information about the article if you want to know more details about this research. So thanks very much for your attention to this presentation.